Okay, we will continue our conversation about definitions of acids and bases, right? And so, right, we've already talked about Arrhenius, who talked about acids as things that increase the concentration of hydrogen ions in water, bases increase the concentration of hydroxide ions in water. And then we talked about Bronsted and Lowry, right? Where acids donate protons or hydrogen ions in reactions, and bases accept, clear that up just a teeny bit, accept hydrogen ions or protons in reactions. And those two concepts are linked in that something can't donate unless there's something else to accept. And so there is an obligate pairing of those two concepts. And so in this one, we will deal with the third major definition of acids and bases. That is the Lewis definition of acids and bases. Okay, for this, we will revisit one of our old friends, Gilbert N Lewis, right? G.N. Lewis. He was an American, right? He was thinking about acids and bases at about the same time as Bronsted and Lowry, but he was thinking of them from a different tact, right? With Bronsted and Lowry, the major particle that defined acids and bases was the hydrogen ion. Lewis was looking for something else. And remember, Lewis was thinking about structure, right? When we talk about, right, Lewis structures, and valence bond theory, those are ideas that we associate with Lewis, right? And so Lewis was thinking about structure, and he was thinking about what it was about the hydrogen ion that made it unique, and then could you relate other things to that? Well, to Lewis, the thing that was unique about the hydrogen ion, right, the hydrogen ion, right, if we think about what it is, right, if we don't just say the words, but a hydrogen ion is a proton with no electrons. Okay? And so normally a proton has electrons in the 1s orbital, right? So its 1s is empty in its valence shell. And so Lewis started thinking about other reactions, right? Right? And so Lewis started thinking about, are there other reactions that occur because species, right? That could, remember, species is a word we use to include molecules or ions, have empty space in the valence shell. I can write today. Ran out of room for my question mark. So when Lewis thought about this, to Lewis, the fundamental acid-base reaction was hydrogen ion plus hydroxide ion. And remember, Lewis was thinking about this in terms of total structure, right? So hydrogen ion, something with no electrons in its outer shell, or at least an empty space for 2 electrons in its valence shell. And the hydroxide ion, something that has a full valence shell, but with unshared pairs in its outer shell. And so to Lewis then, and this is the way we draw it, right? We start with the electrons, turn off the stray mark, right? We start with the electrons, and the electrons from the hydroxide ion move into the empty space around the hydrogen ion to create a new bond. Let's do it this way. So we have H, we have OH, and we have our new bond, right? And so the result of an acid-base reaction is a new covalent bond formed when an unshared pair of electrons from the base goes into the empty space in the valence shell of the acid. And so this is the fundamental basis for Lewis's definition of acids and bases, right? So a Lewis acid has an empty orbital space in its valence shell, right? And then we'll find out later in organic chemistry that some things don't appear to have an empty space, but they can create one, right? And then a Lewis base has unshared pairs of electrons. I can write today. It can share with the empty space in a Lewis, that was a really bad W, acid. Okay? So that's the fundamental basis. But now anything that meets those qualifications, not just the hydrogen ion or the hydroxide ion, can qualify as Lewis acids or bases. And it expands the number of kinds of reactions that we can describe using acid-base principles. So we can have other kinds of compounds. So for instance, right, we can have this compound BH3, which we call borane, right? If you look on the periodic chart, boron only has 3 valence electrons. And so once we get, the 3 valence electrons from boron, the 1 valence electron from each hydrogen, that gives us 6. When we draw our Lewis structure, once we draw those 3 bonds, we're out of valence electrons. And so borane only has 6 electrons in the valence shell of that boron, leaving, let me do it this way, an empty space, right? So borane has an empty space. and could accept a pair of electrons to go to 8. And so one of the ways you find borane is we often find borane shipped with an ether. And so let's just use dimethyl ether. Draw our unshared pairs. This is Lewis, so he would have drawn the full Lewis structure, right? So this is dimethyl ether, right? And so the dimethyl ether, right? The oxygen has unshared pairs of electrons. The borane has an empty spot. If the electrons from the diethyl ether can enter that empty spot and make a new bond, then we can get a result that looks something like this. And I'll draw this in a different color, right? We still have our hydrogen, our boron, our hydrogen, our hydrogen, our oxygen, our methyl group, right? That methyl group, our unshared pair. But now if we go through, let me fix this hydrogen up here, right? A little skittish on the hydrogen there, right? So now, but if we go through and do an analysis of our formal charge, we find out that this boron now has a negative formal charge, and this oxygen now has a positive formal charge, right? And so we've created a new product caused by borane acting as a Lewis acid and the dimethyl ether acting as a Lewis base. Right? And so it expands the kinds of things that we can call acid-base reactions, even though hydrogen ions aren't involved at all. Now, I really like the Lewis definition, right? For us, we will find that the Lewis definition that's what happens when you make a mistake. Definition is most useful in organic chemistry because it lets us classify other kinds of reactions as Lewis acid-base reactions. And when you're talking about more advanced inorganic chemistry, because metal ions often have empty space in their valence shells and can act as Lewis acids to interact with other materials. So it's probably our least important when we're dealing with aqueous solution chemistry like we do in general chemistry. We will have a couple of questions on it on the test, but it's not something we will use regularly. We will most regularly use Bronsted-Lowry and Arrhenius definitions for the way we're going to talk about things in general chemistry. But it is important as you move on in chemistry, especially in organic chemistry, we probably use Lewis definitions more often than any other definition in organic chemistry, and you'll also see it again if you take inorganic chemistry. So those are our basic definitions of acids and bases, right? So just to review quickly, right? So we've got Arrhenius, right? The Arrhenius definition of acids and bases. Acids, when you put them in water, they dissociate or react with the water to increase the concentration of hydrogen ions. Bases, they dissolve in water or react with water to increase the concentration of hydroxide ions. Then you've got Bronsted and Lowry, right? Where acids donate hydrogen ions in reaction, while bases accept those hydrogen ions in reactions, and the two are linked together. That's why I put them on one line, right? And then you've got now Lewis, where acids accept electron pairs and bases donate those electron pairs to make a new covalent bond between the species. That summarizes our three most popular definitions of acids and bases.